nanohub.org.
Online simulation and more for nanotechnology.
All right, the second and last lecture on introducing probability theory. Starting next time, we're gonna be doing more exciting stuff. We'll talk about some of the most common distributions and how to sample them, and the central limit theorem. And then on lecture 6 or so, we're gonna really get into UQ. But anyway, we have to do it just to be on the same page. Remember that there's homework 1 is going to be on this. And some of the things that I have on the slides, you're going to have to derive them on the homework. The derivations are, I would say, trivial, but it may take some time if you haven't done it in a while. So you should start doing the homework right now, not right now, after the class, because it's due on Tuesday, okay? All right, so I'll give you a quick reminder of what we've done the last time. I'll introduce the concept of random variable, and I'll tell you about the basics of discrete random variables, in particular what is the probability density of discrete random variable. Then I'll introduce the basics of continuous random variables. Again, probability densities, cumulative distribution functions, and so on and so forth. And then I'll introduce the expectation of a random variable, which is an operator that acts on it, and it tells you what you should expect from it, and variance of that operator, like the variance of operator. And finally, I talk about conditional independence. When can you say that two things, like two logical sentences, are independent from each other, or that two random variables are independent from each other? Yeah, and if we finish earlier, which I seriously doubt, we will start the handout that we didn't finish last time, but we'll see. Okay, so last time we talked about the interpretation of probability, and we said that we should not really interpret it as a frequency. We can use probabilities to talk about frequencies, but probabilities are not necessarily frequencies. And we started with the example of a coin toss, where we analyzed its dynamics, and we saw that it's not really a random process, but it's a very deterministic process, and that the outcome of the coin toss really depends on the initial conditions. And depending on how well you can control the initial conditions, you can control the outcome of a coin toss. And if you think hard about pretty much any random, quote-unquote, a random variable, if you think really hard, you may be able to explain it using a mechanistic theory, okay? So we said that we introduced a little bit of terminology to talk about probabilities. We said that whenever we see this expression right there, we're going to read the probability of A given B and I, or the probability that A is true given that B is true and I is true. This is the number one take-home message from last lecture. And of course, you should feel free skipping some of the words if you understand, if you keep them at the back of your mind, that they're actually on the background. All right, we talked about the two basic rules of probability theory. The obvious rule, which tells you that if you have one logical sentence, either that or its negation, one of them is going to be true, as soon as it's not a contradiction, of course. And the product rule, which is basically known as a Bayes rule, that tells you how to decompose the probability of A and B. Okay, so these are rules that you should remember by heart. Okay. And using these rules, you can prove pretty much anything you want, like this rule, to which we're not going to give a name, okay? This plus here reads, in case you don't remember, or. Probability of A or B is true is the probability that A is true plus the probability that B is true minus the probability that both of them are true simultaneously. And we introduced the Venn diagram, and we discussed how you can use the Venn diagram to understand these formulas. And this formula, I mean, you can see that if you want the probability of A or B, you basically want to count, to measure this area, and when you add the probability of A and the probability of B, you measure this part right here, the intersection, twice, and you have to subtract it. And that's a way to understand the formulas. Of course, you can understand also the Bayes rule in this way, but we said that these formulas are actually much more general than what the Venn diagram suggests. The Venn diagram suggests that they hold for areas or for sets. They're more general than that. Nevertheless, it's a good tool to have if you don't remember the formula. Anyway, we also introduced this rule, the sum rule. Now, for the product rule and the sum rule together, Bayes rule and the sum rule together, are extremely powerful. And to tell you the truth, you can really, I mean, it's absolutely essential that you know this rule, the sum rule. It's extremely important. Okay, so the sum rule says that you can take any logical sentence you want, A, okay, and then grab a series of other logical sentences, one of which is definitely true, but which are mutually exclusive. No two of them can be true together. And then you can take the probability of A and decompose it into simpler probabilities that you can presumably compute simpler, in a simpler way. Okay, and you can take it a step further by applying the product rule. Okay, and there's a way to understand the sum rule is, again, by the Venn diagram. Please study this, meditate with that. It's extremely important to understand it. So I'm just taking a probability of A and I'm decomposing it based on B1, B2, B3, and B4, which are mutually exclusive, and they make up the whole space. Okay, that's the idea. Anyway, that's all we did last time. Any questions about that? Yes?
What is a color one of the blue parts?
This?
Yeah.
So here I should have you shouldn't really see any blue. Okay? It's an artistic interpretation of the rule. Okay? So that you see that I is on the background. I couldn't make it visible otherwise. Okay? But these regions are zero area. All right, so let's start with random variables. So how many of you have taken a measure theoretic probability theory course? Okay, so you all know that what a random variable is, okay? So in mathematics we say that the random variable is a measurable function from a probability space to another measurable space, okay? That's what we say, which is BS, of course. I mean, why do we need that? Why do we do that? We do that so that, you know, everything we say is nice and consistent, and we can prove theorems. And because we're dealing with things that are continuous, and when you're dealing with continuous things, you have to be careful. Okay, you can show, for example, that probability measures do not exist on cannot be defined on any subset of any space that you like. It has to be a specific set of subsets on which you can define a probability space, a probability measure. But anyway, we're not going to deal about that. What we're going to say is that a random variable is basically a variable of your experiment or of your model or of whatever you're thinking about that takes some values, okay, and you are uncertain about it. That's what we're going to say. Now, to be sure that we're not going to run into contradictions or assume that things exist when they cannot really exist, we're going to say that this random variable, it's either discrete, taking a finite number of possible values, and then everything is nice. We don't really need to worry about measure theory. Or if it is continuous, everything that you're doing, you assume for a nice probability space holds. Okay? This is the assumption. But you shouldn't really worry about that. Unless you're talking about a probability, a random variable whose values are functions or measures or extremely complicated objects, you should not worry about it. If your random variable spits out numbers, then it's nice. Okay? Okay, so discrete random variables are random variables that take a finite or a countably infinite number of values. That's pretty much it. Okay, discrete values. Now we are going to introduce this notation for the probability density of a discrete random variable. So we read the probability that the random variable capital X takes the value small x. Okay, so I'm going to use capital X for the random variable as an object and small x for the values it takes. So this is pretty much like a logical proposition, right? So this is the logical proposition. It's a logical proposition that says x is, capital X is little x, okay? And you ask, what is the probability that this happens? So it's very something that we can talk with using probability theory. And whenever we understand that this capital X is the random variable we're arguing about, and whenever we understand and we know we're absolutely sure about what the prior information is, okay, when both this and that are understood, then we can just write that, P of X, okay? But P of X on its own doesn't really mean anything. You have to connect it to a random variable and to all your knowledge, right? So whenever I write P of X, and I will be writing that, and you should really be writing that because it's ridiculous to write P of capital X equals small case x given I. It's too much, okay? And you cannot even read it. But even though I'll be writing that, you should really be understanding that, okay? For discrete random variables, that is. Now we're going to call that the probability density function, because I don't want to use a different name for discrete variables and continuous variables. But in reality, this is really called the probability mass function. Doesn't matter, okay? So when you have discrete random variable, you have point masses. When you have continuous random variables, you have densities. It's plain with words. All right, the properties has to be positive or zero. Okay, obviously it's a probability. If you sum over all the possible values of capital X, you should get 1, right? So these are obvious rules. Of course, these two are exactly equivalent if you assume that capital X is on the background. And you can also extend the product rule for random variables. So here I'm assuming that I have two random variables, x and y are two random variables, and they're different, okay? They're different. They don't have to be independent or anything like that. It's two different variables of your problem, okay? And I ask the question, what is the probability that simultaneously capital X is small case x, and capital Y is small case y. So I'm asking what is the probability that logical sentence proposition A and logical proposition B are true simultaneously. Okay, so I'm asking this question. And of course, you know that you can use product rule to respond to that question, and you're gonna get probability of A given B, I times probability of B, I. Okay, so it's the same rule. Okay, and this rule, of course, you can just write it like that if you assume that x and y are given. All right, now this thing here is called the joined PDF, probability density function of x and y. It's a probability density function that explains these two variables together, okay? And of course, completely equivalently, you could decompose it in this way. You should get the same thing because the product rule is symmetric. You can do A conditional on B or B conditional on A, you're gonna get the same answer. Any questions so far? All right. So you should get familiar. Hopefully the homework problems are going to help with that. Because I'm going to be writing these things like crazy in lecture 7, for example. Okay? Anyway, you can also write the sum rule for random variables. Again, here what you have is a logical sentence A, the probability that capital X is small case x, and I introduce a bunch of mutually exclusive propositions, namely that capital Y takes a given value. Okay, one of them has to be true because Y will have some value. Okay, and I decompose, basically here we go, I take this probability and I decompose it using this set of mutually exclusive propositions, one of which is true. Okay? And of course you can take it a step further and use the product rule, and you can do this. Just like we did it with logical sentences, we can do it with random variables. Okay? You have to remember this, I'm sorry to say. There's no other way. But if you really think about it, there's one thing that you need to remember, which is the sum rule for logical sentences, and then you just need to know how to apply it to different cases. And if you do it a couple of times, then it becomes obvious that it has to hold. But of course, this is how you will see it in the rest of the course. I'm not going to be writing capital X equals small case x, capital Y small case y, or these i's. I will be writing this. Okay, so you should see this and you should say, okay, yes, makes sense. Okay, so here probability of x is the probability of x comma y summing over the possible values of y. Okay, so you take the joint of x and y and you marginalize out y. So you sum over the possible values of y. One of them is going to be true, and that's what is going to give you the probability of x. Okay? These are all identities, by the way. There's nothing deep about them. They all come from the sum rule on logical sentences. And of course, this, use the product rule here, you can get this. Questions? All right, continuous random variables, where these are random variables that take continuous values, like 2.5, square root of 2, pi, and so on and so forth. What is the probability that a continuous random variable takes a specific value?
0.
It is 0. Why? It is very unlikely if you have a continuous variable to get an exactly one value. Okay? To get to get a non-zero probability, you have to talk about a range of values. Okay? All right, so now let's start. This is the first thing that you should really fill in your handout, is this 0 there. You should remember it. And let's now start drawing a few things. Okay? So what I'm going to introduce is the probability, the cumulative distribution function, CDF. The cumulative distribution function of a continuous distribution, let's say, of a continuous random variable. Okay? So the CDF of the random variable is basically this function right here. It's a function f of x, capital F of x, that gives you the probability that the random variable is smaller than or equal to x. Okay? Now, of course, just by that, and you're going to have to prove this, this is a homework problem. Okay? This is a homework problem. You're going to have to prove that if you plug in that function minus infinity, you get 0. That makes sense, right? Because you are asking, what is the probability that my random variable will be smaller than minus infinity? It is 0, okay? Come on. And that could be a proof, by the way. You can just write, come on. Same thing for this one, okay? So what is the probability that your random variable is smaller than plus infinity? Well, it's 1, okay? Then you will have to prove that this function is increasing. And also that makes sense, right? Because if you take one value, x1, and another value bigger than x2, then the probability that your random variable is smaller than x1 is going to be smaller than the probability that it's smaller than a bigger value. Okay? So I'm just proving it. Okay, I'm just proving it. Now for this one, proving that the probability that your random variable is between two bounds, x1 and x2, that this is the CDF of x2 minus the CDF of x1, for this one, you're going to have to use the sum rule somehow. Okay, you're going to have to find a set of mutually exclusive propositions and decompose that probability so that you get this. What could this be? Well, you think about it, okay? But it's not, so you're going to have to prove this as well. But anyway, using these, we can actually draw that function, okay? So x, f of x, I don't know exactly how it's going to look like, but I know that for very small values of x, how small? Perhaps very small, okay, like minus 10 million, but I don't really know where. It's going to be 0, and then I know that it's going to be increasing, and that it will become flat for very large values of x. So even though I don't know its exact shape, I know that it will look like that, okay? So this is a visual picture that you should have in your mind always when you talk about CDFs. And then let's visualize this probability, the probability that your random variable is between x1 and x2. So if this is x1 and this is x2, this is the probability that your random variable is smaller than x1. This is the probability that your random variable is smaller than x2. And now the difference between the two is the probability that your random variable is between x1 and x2. Okay? I'll give you some time to draw it. All right. So now let's talk about this guy, the probability density function. So the probability density function is just the derivative of the CDF, the derivative of the cumulative distribution function, if it exists, okay, because it may not exist. So the only way this derivative doesn't exist if the cumulative distribution function has a jump. If it has a discontinuity, then that derivative will not exist. Okay? But if it has a discontinuity, then at that point, you can define the derivative using a delta function if you like. Okay? So actually, if you generalize a little bit what you think of a function, okay, if you allow Dirac deltas to be in the class of functions you consider, then you can just always write it like that, okay, and you don't have to worry about it. And this is what I will be doing. Okay, so if I have a step function in my CDF, that means I have a heaviside function centered appropriately. Derivative of that, it's the delta function, no problem, okay, everything works. We'll come back to that later. But anyway, for the time being, let's assume that everything is nice and differentiable and that this derivative exists. Okay, so let's draw this function. I'll show you how this function looks like. Again, it can be pretty much anything, but I know for sure it's going to be positive. How do I know that it's positive? Well, I know it's positive because this guy is increasing. Okay, so it has to be positive. Or 0, because it can be flat. So that's pretty straightforward. So it's going to be looking like that. Okay. It's going to have one bump, maybe it has 2, maybe it has 100. Okay. But it will definitely be positive. So I have an x here and a p of x there. Okay. The other property of the probability density function that is extremely important is that if you integrate it between two certain bounds, it's going to give you the probability that your random variable is within that bound. So if you ask what is the probability that your random variable is between x1 and x2, that probability, if this is x1 and this is x2, that probability is the area below the probability density function. Okay? And of course, if you go from minus infinity to plus infinity, you're going to get to 1 because one of these values is the value of the random variable. Okay? How would you prove that? Well, that's ridiculous to prove. Okay, by the definition of f of x, this is df dx. Okay, and you use the fundamental theorem of calculus, the only theorem of calculus that you should actually remember. Okay, how to integrate the derivative of something. Okay, I'm probably overstating it. You should also remember how to differentiate and integrate, plus this. Okay. Okay, so I will simplify our notation a little bit. I will be writing for continuous variables, I will be writing p of x, and I will be talking about the density, which is of course the derivative of the CDF, which is of course this probability. So whenever we're going to have a continuous random variable, I will be writing p of x, and I will be writing p of x, and I will actually mean the probability density function. Okay, which strictly speaking, this is not really a probability because its units are not probability units. The units of this are probability over whatever the units of x are. So it's a probability density. Okay, to turn it into a real probability, you need to take it and multiply it with a dx, for example. Okay, you multiply it with a dx, and then it becomes a probability. Okay, the probability that your random variable is dx close to x. That's what that probability is. And now if you integrate it over any set you want, it will give you the probability that your random variable belongs to that set. So it's kind of like the density of a body, right, of a physical body. If you want to find the, let's say, mass of a part of a body, you have to integrate the density over that part of the body. Same thing with the probability density. If you can think of, the space where the random variable takes values as a body, okay, and then a specific question about that random variable as part of that body, and then the probability density as giving you the mass, the distribution, okay, you just calculate the mass of that logical sentence. It's the same analogy. That's why we call it a density. Okay. Questions? All right, I can feel that you understand me, and that's great. Great, this feels good. All right, so continuous random variables and the product rule, same thing that holds for the discrete random variables, product rule for the discrete random variables. It actually generalizes to continuous random variables, and it holds for the probability densities. So it holds for the densities. Again here, you know, on the background we have two random variables. This guy here is called the joint distribution, or the joint distribution. Our approach, probably it's called the joint. Okay, one of the two. Same thing, if somebody asks you the following question: what is the probability that x and y together, you know, x and y take values on the plane, right? What is the probability that together they are found on some set A? Then what you have to do is take px comma y, put the dx and the dy there so that you turn them into probabilities, and integrate over the set of values. But this is really a double integral. Okay, and in 3 dimensions it will be a triple integral, 4-dimensional integral, and so on and so forth. Now x and y together, if you put them together, so you can actually define another thing, a z, that is x and y, one after the other, and you call that z, you would call it a random vector. Okay, instead of a random variable. What is a random vector? It's a collection, a finite collection of random variables, one after the other. Okay. All right, and also the sum rule. The sum rule holds for continuous random variables. So if you take the joint distribution and you integrate over y, the process of integrating over y is called marginalizing y. So here I am marginalize y, or over y. And this formula is going to hold. Okay, this is pretty much the same rule, the same sum rule as we had for logical propositions, and we extend it to discrete random variables. It also holds for probability densities. Okay. All right, now let's get back to discrete random variables and introduce the Dirac delta so that I don't have to say that. So what is the difference between discrete and continuous random variables? In discrete random variables, you sum over the possible values, okay, because they are discrete. In continuous random variables, you integrate. Now, there is a way you can describe both discrete and in which you can describe both discrete and continuous random variables in a similar way, so that you just integrate. Okay, so let's take a random variable x that takes discrete values x1, x2, and so on. They can be infinite. Okay, and each one of these values is taken with probability p1, p2, and so on and so forth. So x1 with probability p1, x2 with probability p2, and so on. Then you can write the probability density function or the probability mass function of the continuous random variable if you want. You can write it like that, using Dirac delta functions. Sigma I pi delta x minus xi. So this is a Dirac delta function centered at xi. Okay? So what this tells you is that if you plug in there any number that is not one of the xi's, you're gonna get 0. Okay? Because the Dirac delta function is 0 everywhere except whenever its argument is 0. And its value when its argument is 0 is what? Undefined. Okay? It is not defined. It is not 1. It is just not defined. But, so the Dirac delta function has the following properties. Delta x is 0 if x is not 0, and then if you integrate over a region of space that includes 0, you get 1. Okay? So it basically tells you it represents a point mass, idealizes a particle at 0. This is what it represents. So you can think of this as masses, point masses, idealized as particles, each one with a different mass, the mass here being the probability, and each one of them they're sitting at x size. Okay, and whenever you integrate, everything is going to work out fine with the Dirac delta function. So now you can just be integrating, and the Dirac delta over all x's, and the Dirac function will ignore everything that is not xi. Okay? But anyway, it's not really, it's just to simplify our notation. So now I'm allowed to not specify if my random variable is continuous or discrete, and as a matter of fact, it could be a mixture of discrete and continuous, and I can just integrate. All right, so now let's talk about expectations of random variables. So far, do we have any questions so far? All right, so expectations of random variables. We're going to be writing expressions like that. Let me just show you how it looks like. Now I'm very particular about this. I like this E to be different than this E. I don't like an E without a second vertical line. Okay, because in many applications that E is reserved, for example, for energy or for something else. So let's not use it. You just draw one more line there. Okay, and this is the math BBE. And you can define in your own command so that it is E. If you don't know what I'm writing about, I hope you're not a PhD student. But anyway, I'm kidding. You will learn about that at some point. I'll let you use Word. So, what is this thing, the expectation? It's actually, okay, you should think of it as your expectation about what the random variable is going to be if you had to pick one number. Okay, if somebody told you, okay, what do you know about X? But you have to pick one number. You can't tell me, I know its probability density, I know that it's with high probability between that and that. No, give me one number. What number should you pick? That's actually something, to answer this, you should probably take Professor Panson's course. But let's say, simplistically thinking, you should pick the expectation. If your loss for making the wrong prediction is the square loss, you should pick the expectation when somebody asks you to give them one number for your prediction. But it is, and the expectation is defined as follows, right? It's x times p of x dx. You remember from mechanics when we take the center of gravity, right, or the centroid of a body, we're doing x times the density. It's the same thing, okay? Only now we don't have to divide. We don't have to divide with px dx because this is 1. Okay, it's already done for us. Okay, so it's kind of like the central value of your body, right? Of your random variable, the central value. But of course, you remember that in a body, the center of mass doesn't have to be a point on the body. Okay? Same thing here. The expectation of a random variable doesn't have to be a value that the random variable actually takes. So if somebody asks you to predict, to give a single value for your prediction, you should be a little bit careful if you decide to pick the expectation. So just if I'm asking you, okay, here's an object, an object, and I ask you, where is it in space? And you tell me it's wherever its center of mass is. That's fine. Okay, but what if the center of mass is not a point of the body, right? So if, for example, if your body is like this, then the center of mass is here. Okay? So you're reporting a point that is not on the body. Let's see this problem with the expectation. So let's draw two different distributions, x and p of x, and I'll have another one here, x and p of x. Okay, so I'll give you here a nice distribution, nice in the sense that it has a unique mode. That's how we call this guy, we call it a mode. Okay, it has a unique mode. So if you, this is kind of like the density of a one-dimensional body, right? Where is its center of mass? It's right here, okay, right here. So the center of mass or the expectation will be somewhere here, a little bit to the right of the maximum, okay, but it will be around there, okay. So in this case, if your prediction about the value of the random variable is the expectation, you're probably doing a good job, depending on how narrow this is, okay. But here's another possibility for your random variable. It could have a density that has two bumps, okay? Two modes, mode number 1 and mode number 2, okay? Now the expectation is going to be here. The expectation for the random variable will be here. So the expectation will be at a region of the value space that has 0 probability density. It will be at a value that your random variable will basically never take. Okay, so then that is a ridiculous prediction, right? And that's why, you know, predicting the mean, if you're sure that you have one mode and the spread is small, then predicting the mean is okay, but you should not just predict the mean. You should really think about other stuff than the mean before you make your prediction. And you can imagine that in higher dimensions, it's way more complicated than that. Okay? Any questions? Yes?
So why do we not just take the maximum of the probability distribution?
This is a very good point. Then the maximum, this is another way of looking at that. The maximum would be here, right? And the maximum for this one would be here. But now this particular random variable will be found here 55% of the time. So 45% of the time you will be wrong. So the answer is, probability theory is not enough for telling you what to pick if you have to pick one number. It is not enough. You need decision theory. So you need to quantify what is the cost you incur if you make the wrong prediction, and then try to minimize that cost. This is the right way of doing it. And of course, different people will have different costs. If you are okay making 45% of the time the wrong prediction, then by all means, go ahead and pick that. But maybe, you know, a more robust strategy would be to actually not pick one number, but randomize your choices. I mean, what if every time you need to pick, you don't just pick one deterministic number, but you know, 45% of the time you pick this pick, 55% of the time you pick that pick. Actually, if you do something like that, you may be able to reduce your cost by randomizing your choice. Anyway, but it's really, it's a course on its own, okay? Professor Pansal is doing that course. Every 2 years or every year? Every 2 years. Next, 2019, fall. All right. Any other questions about this? Yes.
Like we already discussed that the probability of a point in a continuous thing is 0. How are we getting an expected? How can we say that?
Okay, let me say that the probability of, let me restate it. You're absolutely right. And the probability of getting this prediction is also 0. Okay, getting it exactly. That prediction is 0. But the probability of getting something, let's say delta x around that maximum is quite high, like 20%. The probability that getting delta x something around this is 0, or very close to 0. Okay? but I will be making, this is what I meant, but I don't want to use too many words. All right. So some properties of the expectation operator. We'll do a few proofs just to show you what you should be, you are expected to do in your homework. This is just for you to remember what you should already know, okay? Because after today's lecture, I'm just going to be using this stuff. All right, so how do you prove that if you take the expectation of a random variable plus some constant, then that's the expectation of that random variable plus that constant? This is just a property of integration, right? So if you look at what this means x plus c px dx. And, well, that constant, you can actually, use this property of the integral. And then you know that, this guy is the expectation of x, of course. And then you can take the constant out of the integral. Everybody knows that. And then this guy is 1. Okay? Now, this is the level of detail that we need in the homework. Okay? All right, what about this? This is a little bit trickier, so let's do this as well. So now I have two random variables, capital X and capital Y. And the reason I'm doing that is because I want to tell you what this expectation actually is. And it's a good opportunity to do that. So the expectation of X plus Y is the expectation of X plus the expectation of Y. Questions? Yeah.
Does this assume independence?
No, for any random variable. For any random variable x plus y, x and y, this will hold. So let's see it. This is the following integral, x plus y, and then here I have to put the joint probability density, px dx, px comma y dx dy. You see, it's not just one of them, it's both of them together, okay? So I'm gonna have to now decompose this integral. Of course, I can use this, the sum rule of integration. Okay, to write it like that. And I'm kind of stuck, right? So now I need to show that this is actually the same as that. Okay, so let's show that. Let's pick one of them, because for the other one you do the same thing. So let's pick this guy. And let's show it. We have x, px, y, dx, dy. And the only thing that we can really use is the product rule, or the sum rule, or the obvious rule, one of these things. So I'll use the product rule. Okay? Now the product rule, I can condition on y or I can condition on x. I'll just condition on one of the two randomly, and if it's not working out, it's the other one. Okay? All right, so I have integral. It's a double integral, so let me just show it as a double integral. X, I'll have here p x given y, py dx dy. Okay? Is this going to work? We're going to have to split the integrals, and we need to be able to do one of the integrals. I should have brought my notes. All right, so let's see if we can split the two integrals, x, y, dx. Okay. Okay, now I see it. You know what? I'm not sure. Let's work out the other one as well. It's a funny thing that when I do it on my own, I get it, and then when I do it in front of 50 people, I cannot do it. So let me just look at what I did. Okay, let's make sure that I haven't made a mistake. Yeah, actually, it's much easier than that. What am I doing? It's amazing. It's your block. It's ridiculous. Okay, it happens. Okay, it happens. It's very easy actually. I can first integrate over y, and y was going to disappear. Okay, sorry about that. So look at that. Let's put the integration of x outside, right, like that. And then inside, I'm going to have the integration over y. So here we go, integration over y of x px, comma y dy. Okay? Everything is okay with that because this is how we do double integration. Okay? It's a little bit more complicated because we have to specify the domain and all that, but here the domain is R2. Okay? So this is, are we okay with that? Yeah, I confused myself by talking too much. And then this integration right here over y, I can treat this x as a constant with respect to that integration, so I can take it out. Okay? So let's see. I can take that constant out, x times pxy dy times dx. And here's now our sum rule, right? So you have the joint distribution of x and y, and you're marginalizing out y. What are you going to get? Px, right? So this guy here is p of x, and this is going to give you now x p of x dx, which is the expectation of x. Okay? But you see that even I don't remember all the proofs by heart. And they don't come to me all the time, okay? Have to be in a quiet place alone for them to come, all right? Anyway, the same thing you can do for this one. So you can show that this formula holds for arbitrary random variables. And as a matter of fact, what we can show is that it holds for any random variables you want. You can take as many as you want, n, but let's make it finite, and it will still hold, okay? And this is going to be the basis for developing Monte Carlo techniques. What else can you do? Yeah, that's pretty much it. Okay. Any questions? All right. This one is actually much simpler, and I should have done it first. All right, so it's this integral cx px dx. C is a constant, it comes out, x px dx, and the formula follows. Okay? But I would say that for the expectation, right, this formula you probably need to remember that the expectation is a linear operator, okay? Okay, so this is a generalization of the expectation for arbitrary functions of the random variables. So this is not a definition. This is not a definition. This is actually something that we prove that is valid, okay? So, and it goes like that. I'm not gonna do the proof because honestly I do not remember how it goes, and it is just analysis. So if x is a random variable, and then you take any function of that random variable x and call it y, that y is also going to be a random variable, okay? So then you can ask the question, what is the expectation of y? And that's exactly what we mean by the expectation of g of x. Okay, and of course the expectation of y is yp y dy, which is g of, which is that, okay? And then what you do is you change variables to your integral and you say, well, I'm going to define x to be g minus 1 y, assuming that it's a one-to-one function, and then dx is gonna be, d of g minus 1y, and then that is gonna give you gx px dx, because some of the normalization, some of the constants of the terms that appear will cancel each other. But this thing here is a theorem. Like, we would spend like a lecture on proving it, okay? But you can take it for granted because it's kind of obvious, okay? So if you want to find the expectation of a function of a random variable, then you just do this integral, okay? And we'll be using this constantly. It's a very useful formula. All right. Now here I want to make a very important point. This is called Jensen's inequality, and it tells you that if you have a convex function is a function that looks like that, okay? And you do f of the expectation of x, then that is going to be less than or equal to than the expectation of f of x. Okay, so far so good. This is what happens for convex functions. For concave functions, the opposite happens. Okay? It's not important to remember this formula because you can always look it up. If you need it, you probably never need it. But what you have to remember is that the equality does not hold. Because I have observed, in my experience with engineers, that we have the natural tendency to just, if somebody asks us to find the expectation of f of x, we have the tendency of saying, okay, let's take the expectation of x and plugging into f, we should get the same thing. Okay, well, you don't get the same thing. You can get something smaller if your function is convex. You can get something bigger if your function is concave. You can get something that you cannot really predict what it is if you don't know what your function is. Now, if you have a linear function, then you're going to get exactly the right answer. Okay? So only if this is a linear function, you can actually just plug in the expectation. Okay? Or if you take the Taylor expansion of your function and you are considering very, very small variations, then you can do it. All right? So even though you don't remember the Jensen inequality, do remember this. Okay? And resist the temptation of just plugging in that expectation. All right. Now, the variance operator is another operator that I want to introduce. It's defined like that. It's the expectation of the square distance of a random variable from its mean. So you measure how much around the mean you spread. And I will not go through a lot of details, but I'll just show you two different distributions. So this distribution, for example, has a small variance. The variance, if you like, and we'll talk about it later, kind of measures this spread about the mean. Okay? And then I'll give you a distribution with a higher variance. Here it is. Okay? So that distribution will have high variance. Has a bigger spread around the mean. Okay? And of course, again, the variance makes sense if you have a distribution that has a unique mode. Because when you have two modes, it's kind of meaningless to talk about spread. Okay? You need more information than just one number. Any questions about this? So why did it go down? Why did the probability density function go down? Okay, Alana. The area has to be the same, so it has to go down. Good. Okay. So this is a homework problem to prove this formula. Okay, that the variance is the expectation of the square minus the square of the expectation. This is, if somebody tells you compute the variance of this random variable, that's how you would do it. Okay, you would first do this expectation, and then you would do that expectation, and then you would apply this formula. Okay. Now the variance has certain properties. One property is this: if you add a constant to the variance, this doesn't matter. Okay, so you're just basically translating your random variable, and you center it at a different place. Okay, or you change your coordinate system or something. All right, but if you take a random variable and you multiply it with a constant, then that constant comes out squared. And that's very easy to see. I mean, if you look at the definition of the random of the variance, it is like that. Okay, so if you put a C here and there, to take it out, you're gonna have to square it because of this guy right there. Okay, so it's trivial. Another thing that I would like to introduce is the covariance operator. I know it's very dense, right? But I'm actually saying everything I want today, so we're good. So the covariance operator measures to what extent two random variables x and y change together, okay? And I'll give you some extreme cases. So if the covariance of x and y is 0, then we say that the two variables are uncorrelated. Be careful, not independent, because that's different. We say uncorrelated. What does that mean? That means that if you try to draw samples from these random variables, these samples will fall on a blob, like that. You will not see any obvious trend. Okay? If the covariance is positive, then that means that x and y vary together, okay? Which means that if you draw samples from these random variables, the samples will show kind of like a trend like this. Doesn't have to be exactly a linear trend, but it will kind of be like that, okay? And if it was negative, then you would get a trend like this, okay? This is going to be an extremely useful operator to us when we talk about Gaussian processes later on. Forget about it now, okay? But we'll revisit it. Okay, so properties, you should review them. You should be able to work them out. They're fairly easy. This is something that you need to pay attention to when you have, so the variance operator does not behave exactly like the expectation operator. It has this thing right here. Okay, so the variance of x plus y is the variance of x plus the variance of y. So far so good, but you have to add that 2 times the covariance. Now only if the covariance is 0, the variance is additive. Okay, so if the variables are uncorrelated, the variance is odd. Anyway, you can. There's no reason why you can extend the expectation operator to conditional distributions. So you can write things like that. Let me take the expectation of x if I know that y, which is another random variable, is exactly small case y. Okay, or any other kind of information, you can use it to condition your expectation operator. And what does that mean? That means that when you the density you use here is the conditional density. All right. So if you have here, if you knew that, peanut butter, whatever that means, I don't even know how to spell peanuts. I guess like this, peanut butter, I'm getting tired, you would just condition on peanut butter, okay? Whatever. And you can extend this idea to other operators like the variance. So you can say the conditional variance, which is the variance I would have if I went wherever I have my probability density, I replaced with a conditional probability density. Okay? Okay. 10 minutes now to talk about conditional independence, and that's it with probability theory. I know that at that point you are probably just want to go for lunch, of course. So just make sure to come back and, you know, look at it on your own, all right? But I'll still go through it, yes.
Correlation and covariance are two different values, correct?
Yes. So the question is covariance and correlation different? Yes. But the correlation is defined as the covariance divided by the variances of the two random variables. So a correlation is a normalized covariance, okay? All right, so conditional independence or independence of logical sentences or random variables. You're going to have to prove things about this in your homework. I'll tell you what exactly you're going to have to prove. So here I start with two logical sentences, A and B, and I'm going to use this symbol here, it's orthogonal symbol, to say that A is orthogonal to B, meaning that A and B are completely independent. A has nothing to do with B. They are, if you know A, you cannot really say anything about B. If you know B, you cannot really say anything about A. Okay? There are a lot of things like that. I don't know, the weather in West Lafayette is sunny, and in my pocket I have $0. Okay? Yes. They're completely independent propositions. Okay? It's an extreme example, but you get it. There are a lot of things that are like that. But anyway, the important thing to observe here is this I, the conditioning information. So we're going to talk about independence of two things given all the information that we have right now. And I'll tell you what I mean by that in the next slide. But here, this is what independence means. This is how we encode it mathematically. We say the probability that A of A given B is the same as the probability of A without knowing B, because B doesn't tell us anything about A. Okay? So this is how we define the conditional, the independence of two logical sentences. So basically, it doesn't matter that you condition with B because B is irrelevant. Okay? That's all it means. This is different than what you would see in mathematics, in a mathematical course. In a mathematical course, you would say this. Okay? Two random variables are independent if their probability density is factor. Which is, again, it's BS, because it doesn't make sense. Unless this is what you're talking about. Unless you prove this, then it does make sense. Okay? But you can just start there and prove that. Okay? So you can show that if two random variables are independent, therefore this holds, this is equivalent to their probability densities factoring. To the probability is factoring. So probability of A and B is the probability of A times the probability of B. Okay? So this is a homework problem that you're going to have to prove. Okay, but I really want you to think about this, because this is the only way to understand independence, is thinking about this expression. All right. Now I want to introduce conditional independence. So A and B can be independent if you observe another variable C. So to understand that, think about the following case. Assume that we have three random variables, C, A, and B, and C is the common factor of A and B. Like C affects both A and B. So of course, if you just look at A and B, they are correlated. They are not independent. They have a common factor. How can they be independent? Okay? But if you observe the common factor, if you know what the common factor is, then they become independent. Okay? This is something that you need a little bit more than 3 minutes to understand. Okay? And have we put this in the homework? No? I'll put it in the next homework. Okay? So in the next homework, I will ask you, because it's important, to find examples of, two things with a common factor, and then argue how observing that factor will make these two things independent. Okay? But again, the formulas are exactly the same, so you see that this means that the probability of A and B, of A conditional on B and C, does not depend on B. B disappeared. Okay? This is what it means. So if you observe C, you don't need B. And it makes sense if you look at it here, right? Look at it here. You are asking, what is the probability of A given that I know B and C? Well, if I know C, then I don't need B because the arrow goes this way. Okay? This is what it means. Anyway, and then you can show that this holds as well. That, namely, that the conditional probability factors for A and B. This conditional independence idea can be extended to random variables, and again, for probability densities, if you have two random variables x and y that are independent, then their density satisfies this. If you try to condition on y, well, y doesn't matter. Okay, that's what it means. The joint probability density is going to factor. This is another formula that you can prove. If you take the expectation of x and y, multiply together, that's going to be the expectation of x times the expectation of y. This only holds if the random variables are independent, otherwise it doesn't hold. And how do you prove that? I mean, you just integrate. There's a theorem called Fubini that allows you to do a double integral by multiplying two single integrals. And the other thing that you can show is that the covariance of two independent random variables is 0. Okay? So if they are independent, they don't vary together. But notice this. The arrow goes only one way. If you have 0 covariance, this doesn't mean that the variables are independent. As a matter of fact, they can be deterministically tied together and still give you a 0 covariance. And I will show you examples later. But if you know, for example, more things like that x and y are Gaussian, then it is sufficient to say that they're independent, but let's not get there. Let's just say that the arrow doesn't go both ways. Now, if the random variables are independent, then their variance adds up together, and this is something that we're going to use when we talk about Monte Carlo. And I just give you 30 seconds for free to do whatever you want with it. Any questions? Yes?
So for the expectation variance terms, the plus sign and the brackets, that doesn't mean or, that means something else.
Which brackets?
Yeah, on the left side of the brain, so the expectation of the bracket.
This means, whatever is inside the brackets is the argument of the expectation operator, the square brackets.
But if it's a plus, so you have x plus y, so x times y, that plus doesn't mean or does that mean?
Oh, that plus means an actual summation. Because x and y, now they're not logical sentences, they are random variables, so they're supposed to be numbers. Okay, so obviously that plus sign needs to mean something, it means a number.
And then x and y in that case is sort of like probabilities of x and probabilities of y?
No. Okay, this is a good question. It's on the meaning of the expectation operator. So what goes here is the random variable, and you should think of the random variable as something that describes something about your problem, and it carries with it a density. Okay, it carries with it its density. So this means x px dx, and that px is inside the random variable. Okay. Now, when I say here x plus y, what I mean is take these two random variables, add them together, and create a new random variable, call it z, find the density of that random variable, and integrate it with respect to that, the sum. Does that make sense? It just happens that if you do that, if you call this z and you do this, it just happens that it is actually the same as doing this. Okay? But I don't have a semester to explain why. So we're gonna have to, just feel the formulas. And eventually you will just like them, I guess. All right? They will become familiar eventually. All right, guys. See you on Tuesday.